participants, welcome again to the Wadla 3.0 workshop. So now we are going to start 29th session on day 4 of Wadla 3.0 on topic recent trends in deep learning and applications. So today we have Mr. Siddharth Sharma from Amazon. So he is going to talk about real-time inferencing deep learning models. So before starting his talk, so I would like to introduce him. So Siddharth Sharma is a machine learning tech lead at science and modeling team at Amazon Music. He specializes in search, retrieval, ranking, and NLP-related modeling problems. For around a decade, Siddharth is working on large-scale machine learning problems that are latency sensitive. It means ads, targeting, multimodal, retrieval, search query, understanding, etc. Prior to working at Amazon Music, Siddharth was working at Fortune 500 companies like Meta, Walmart Labs, Rakuten on e-commerce centric ML problems. Siddharth spent early part of his career working with Bay Area EdTech startups. Once again, welcome Siddharth to join these wonderful sessions of Wadla 3.0. Now the session is over to you.
Shall I start sharing my screen?
Yes.
Yeah, give me a second. Just to confirm, are you seeing the presenter's view or the presentation?
Yeah, we can see your presentation.
Give me a second. Cool. Just the presentation part, just not the notes and the other components. Are there?
Yes.
Yeah. So yeah, let me start. Hi everybody, my name is Siddharth Sharma. The focus of this talk will be on inferencing of deep learning models. The agenda is divided into 5 parts. In the first section, we'll go through the need for focusing on custom inferencing. The second part will focus on what comprise of high-level architecture of model servers and the components of modern-day model servers. The third part of the talk will expand on benefits of GPU-based inferencing. In the fourth section, we would go through some interesting optimization and model format level that can speed model inferencing. And last but not the least, we will go through state-of-the-art techniques developed in 2023 this year to speed up model inferencing. Yeah. So starting on the first section. So as you see, it took Facebook almost 4.5 years to reach 100 million user mark, while it took TikTok 9 months to do the same. Now, GPT's adoption has been explosive, reaching the 100 million user mark in 2 months. After this breakthrough, we saw massive investment in development of proprietary and open source LLMs like Llama, Bard, etc. Now, LLMs are being used for chatbots, information retrieval, summarization, content curation, etc. So now the question is, will sending prompts to OpenAI's APIs suffice all use cases? Now, when this question was asked to billion-dollar plus companies or other smaller companies, like what are the challenges they see associated with leveraging LLMs in production settings? So companies responded with concerns around prediction accuracy, cost, and privacy. Now, in this chart, you will see that large companies are more sensitive about privacy concerns and concerns about data governance, compliance, and bias, whereas smaller companies are more concerned about cost factor.
He's coming.
Now, to mitigate the concerns and issues associated with usage of LLMs, a plethora of techniques has emerged, especially in this year, in 2023. Now, the key idea around all these techniques is centered around domain adaptation. Now, here, let's say you are a law firm, a finance firm, or a health insurance company, and you want to make your use, let's say, some LLM as a chatbot, or even a, let's say, there are lots of companies which were earlier working on HR chatbots. This was a very hot area for the last couple of years. Now, if you want to just use LLM on that, that won't work, because these pre-trained LLMs are not aware of your data. Now, this lack of understanding on company-centric or custom data, now this creates a big challenge for leveraging their full potential. That's why lots of techniques like fine-tuning these LLMs on your custom data sets, using low rank adapters or retrieval augmented generation, which is commonly known as RAG, which basically benefits from vector search. These are heavily being adopted across industry. So what I want to state is LLM's usage are not just restricted to prompt engineering and using APIs by third-party provider companies like OpenAI or some Bard API or something. So a lot of companies are investing in-house, whether small or large companies, in fine-tuning them and creating custom model checkpoints. Now, if you look through the timeline, that the first half of this year and the second half. So OpenAI released ChatGPT last year around the same time in December. So after that, we saw an explosion in a lot of open source and proprietary LLMs, but especially Llama and Mistral are two biggest name in open source LLMs. And we are seeing that a lot of companies are fine-tuning these LLMs for their custom use cases. Now, this creates an interesting problem hosting these custom models and performing efficient inference on them. So these models are like, even the, I will say, if you take, let's say, Google's T5 large language model, even the, I will say, the smallest checkpoint, T5 base, is around 250 million parameters, whereas the larger checkpoints for Llama are 7 billion, 13 billion. So they're extremely large models. So even if you fine tune them, let's say using lots of computational horsepower on your custom data, the big challenge will be how will you host them in a cloud solution or your in-house servers. Now, when we talk about hosting a model in-house and inferencing it, so what does inferencing involve? Is it just like calling some simple PyTorch APIs, loading the model, and just calling like execute or inference? Now, in the next section, we'll go through some high-level architecture of model inferencing and its core components, core involved components that are needed to basically do model inferencing at industrial scale. Now, this is a very high level, I would say, bird's eye view of a model inferencing workflow, where you have any deep learning application, whether it's a image classification application or text summarization, or like a chatbot-like application. So you have a user-facing application, then you have a application backend, and then finally, all the model inferencing, I will say, infrastructure is hosted separately. Why this is hosted separately is because the computational horsepower it needs, and it's better to all the logic of model inferencing and lots of interesting details is better to separate these services out from your core application backend architecture. Now, taking a step back and thinking What is a model before we jump into inferencing side? So any deep learning model these days, let's say you are using PyTorch or TensorFlow, when you save the model, you will see if you look at the output of the saved model on your disk, you will see that it has two components. You have the model data part, and you have the the architecture. So overall, a machine learning model, deep learning model is just a, when we say model, it's just an executable program which these two components. The data part contains all the trained weights, the biases, the vocabulary, embedding layers, uh, and other necessary metadata. And the prediction algorithm, the architecture is just the neural network architecture that you're using. It can be a transformer architecture, it can be a resonant architecture. So when you store the model, you have these two components, and when you load it, so first the architecture is loaded and is initialized with all the weights and other data part. Now, jumping ahead, when we say inferencing, what we mean by that? So it means we already have a trained model and we want to provide an input in real time, and model parameter and everything, anything is not changing. We just want a forward pass on the model graph and want to get the output. So as you see here, so we have an input request. It can be a text or image depending on this image model or let's say language model architecture. So at very high level, the core components are, first you need a input output layer, which is your interface layer. It can accept like HTTP requests or RPC requests, and then you have a model inference graph which have been initialized with model weights. Let's say so you have a model training job on the right. So you have that model will be trained, and the output, as we said, that the model graph and the weights will be saved somewhere. So your model server at very high level will basically ingest the model graph and the weights, initialize it, and then in real time you get the request, you pass through the model graph and respond the output. So this is what we mean by inferencing. Now digging deep into this part, so expanding more on the components, how model servers are different than, let's say, your web servers or application servers. At very high level again, we have on the left hand, let's say we have the request. You have the web interface layer, which can be a HTTP or a gRPC or another kind of RPC protocol. Then, like any web server, you have queues. So if, let's say, you are receiving input requests at very high rate, so requests will start getting queued here, and then there will be dispatcher threads, which will basically take batches of requests and submit to the pre-processing step. By pre-processing, we mean just to give you an example. Let's say your input request was a simple, let's say, sentiment classifier model. So you got the text. Now, for your model to do inference on it, you need to first tokenize it. So that will happen at the pre-processing stage. Your text will be tokenized, and the tokenized vector token ID will be forwarded to the model, and model will make a prediction, but the prediction will be in token IDs. Then again, you apply the tokenizer decode step, generate the text output, and you basically, or your label, and you return the answer. So now, to put it formally, this is I will say very component level architecture, core components with lots of abstractions of a model server. You have some application. Again, as I was explaining, we have this endpoint, the second step, which can be HTTP or gRPC. Then you have a queuing service. Then you have some thread pool, which is creating batches or requests and submitting to the model. And along with that, you have your metric server. It's this is just a standard component where it will log like how many let's say memory is being utilized right now, how much CPU is being utilized, how many requests, what's the latency of request, what's the queue size. It will monitor everything and keep on logging so that you'll get a glimpse into what's happening under the hood. And then you have your compute hybrid and model framework. So now In this all this high-level workflow that we saw, how a model server operates, going to the core part, which is this model and this inferencing part, the hardware interaction. Why do you think that the most compute intensive operations when it comes to inferencing, like when we have a neural network and we do a forward pass, especially uh, concerning, let's say, transform models, because these are almost used everywhere these days. These are de facto architecture. So in any, let's say, BERT style model, transform model, when you do a forward pass during inferencing, what kind of operations do you anticipate? Now, at very high level, we have three core operations occurring in especially transformer architecture, which are very compute heavy. These are matrix multiplications. When you do a forward layer in a neural network, or you have multi-headed attention, all that is happening in those layers, and attention layers as well as forward feed forward layers, are matrix multiplications. Then you have, so we call in more formal language tensor contractions, the matrix multiplications. Second is statistical normalization, like the last layer. Let's say you have a language model head, the softmax layer, or you have a classification head, again, softmax layer. Along with that, you have batch normalization, layer normalization kinds of techniques in the transformer architecture. And last but not the least, you have biases, dropouts, residual connections in the transformer architecture. So these are element-wise operations. By element, we mean, let's say you have a vector and you're applying, let's say you're applying sigmoid to each output, let's say, each value. So you're not doing any multiplication of a vector or a matrix, or you're not doing some normalization technique, but you're applying some function to one particular value. Let's say you have the output plus you are adding the bias layer. So it's element-wise addition. Now, a quick question. Of these three operations that we just saw, the matrix multiplication, normalization, element-wise operators that are applied during the forward pass in a transformer architecture. Just I will say, guess what are the proportion of these operations? So, to everybody's surprise, these are the numbers. Like when we do a flop count on BERT for what are the basically all the computational horsepower, where it is used, in which operation, you will see that majority of the floating point operations, the flops, 99.8% are consumed in tensor contraction, the matrix multiplication. Rest of the layers or rest of the operations in a transformer architecture, which involve, let's say, softmax layer, the activations, bias addition, and layer normalization, doesn't even account to 0.2% of the rest of the computational, I would say, consuming the rest of the computational horsepower. Now, as we saw, extreme majority, 99.8% of computation is being used by just the matrix multiplication during model inferencing. Now we know that, but matrix multiplication is inherently embarrassingly a problem which can be, like they call it, embarrassingly realizable. And what is good at matrix multiplication? What kind of hardware? I mean, what hardware can basically very efficiently parallelize? If a operation is parallelizable, it can execute it like very efficiently. So here comes GPUs. So compared to CPU, which have like several order less flop capacity, mainly in gigabytes, and if you even consider the most advanced CPU, the Intel Xenon, it has 1 teraflops compute capacity. By teraflops, we mean like 10 to the power 15. So now if you look at A100 GPUs, which are MPA generation, the latest NVIDIA GPUs, after that they have introduced H100 also, but A100 is very widely used across. If you go to AWS or Google Cloud, I will say the all these big models, the Llama 13 billion parameters, 7 billion parameters models, or the T5 architectures, almost all applications are consuming 800 GPUs right now. They are very, very fast, and they have like almost 40 to 80 GB, depending on the variant, memory RAM. So these GPUs can, compare to the CPU, what we saw, the most powerful one is 1 teraflop, but majority are like in gigaflops, can perform in FP16, the 16-bit floating point data type, which is heavily used during training and inferencing. We can perform like 312 teraflops operations, whereas in FP32, it's around 19.5. So GPUs excel at matrix multiplication operations. They have specialized architecture, which is called tensor core GPUs, that is built for matrix multiplication. Same thing with Google's TPU architecture. Now, before jumping ahead, there is a very interesting problem that comes with GPUs. So this is, let's say, very high level architecture of GPU. So when we say a GPU has a, let's say, 40 GB RAM, 800, and your whole model architecture and weights are stored here, but to compute, it will have to read from the RAM, the DRAM, and take it to cache and registers, and then compute. So earlier we looked at the teraflop capacity of 800. It was like 312 for FP16 and 19.5 for FP32. So in 1 second, it can do 19.5 teraflop operations. Whereas the speed at which it can read the data from these, from its RAM, I'm not even talking about getting the data from CPU. It's just reading from the RAM, is 1.5 terabytes per second. It means in 1 second, the GPU can do 400, it can load 400 billion numbers in memory, let's say floating point numbers, but it can perform 20 trillion operations on them. So majority of the time when you are doing inferencing, or a lot of time during training also, you will see, if you run a profiler, that your GPU is just sitting idle. So it will be, your usage will be like 30%, 20%, 80% will be underutilized, because your system is just busy reading data from CPU or from GPU DRAM to the caches. Now, this very interesting challenge. The question is like how to get around this bottleneck. Now, here comes our next part of our presentation, the model format optimization. What can we do when we train a model, and let's say we train a PyTorch model and we have saved the model, and it's in PyTorch script, let's say, the format. So what we can do to change the format in a way that is much more suited to GPU inferencing. As we saw, the main challenge was the GPU memory capacity first, and then second is the read write, the IO, I will say bandwidth. So one very efficient and quick technique is, when you have trained a model, you do quantization. It's post-training quantization, where you have a model and all the model weights are in floating point 32 bits. So normally when you, there has been a lot of research that when you train models, the weights are very, the range mostly lie in -1 to 1. So you don't need 32 bits to represent those numbers. So a very quick, I will say very fast and easy way to increase the efficiency or inferencing pipeline is convert your model to FP16 format. So in quantization, we will basically normalize each weight, the 32-bit weight, in we'll scale it, sorry, in FP16 range. Now, first of all, your model size will shrink. It has almost become half. Second, as I was explaining earlier, that GPUs like 800 are way faster in computing on FP16 than FP32. FP16, I think about 12.5 something teraflops, and here is 312 teraflops. Is orders of magnitude computational speed. Second thing, so these are all, in a way, you can think of these as compile time optimizations. And when you have trained a model, you saved it on test. Now you're applying some steps to improve its format in a way which is much more suited for inferencing. The second is layer and tensor fusion. So let's say you have this a ResNet kind of architecture where you have these convolutional blocks. uh, so you have the convolution, then you have the bias, then you have the nonlinearity applied. You have different kind of convolution filters, and you're doing pooling operations and convolution filters, then the bias, then the nonlinearity, then you are further processing them in higher layers. Now, when let's say we have these operations and we took our input data, we are reading from CPU to GPU RAM, then GPU RAM to caches, then we'll perform one operation, convolution. So GPU will, then the computation, the result of this will go back to GPU RAM, then to CPU, then the next operation will be submitted. So it's lots of to and fro's when GPU is computing. So what you can do is, during compile time optimization, NVIDIA has a very awesome model format called TensorRT. It will, during compile time, it will ingest your PyTorch model and try to find, it has already hyper specialized CUDA functions, CUDA kernels, which for performing the whole block of operation in one go. So it'll take the input data, and it's like multiple, the FOG kind of thing. Like first you are applying this function, then on the result you are applying this function bias, then on the output of the bias you're applying ReLU. So in one go, you have this whole block of operation. So you don't have to, in a way, up and down, you don't have to go back, compute the output of one transformation from GPU, then submit it to GPU RAM and CPU, then get the output again. It will read the same output again and apply the bias function. So instead of that, in one go, you are performing multiple operations. So this is basically you are merging all the layers. It's called layer fusion. Similarly, you have tensor fusion. Another more of compile time optimizations are kernel auto tuning, which again the NVIDIA TensorRT tool utility is doing. It will at compile time, it will select, depending on your hardware, what kind of GPU you will be using during, let's say, inferencing. It will have custom code CUDA kernels that it will bind that for, let's say, matrix and vector multiplication, use this function. That can literally scale your operations on GPU. It will parallelize it and exploit the best out of that particular GPU architecture. So for each GPU architecture, they have different kind of CUDA kernels, which are basically the functions which we execute on GPU, so that GPU hundreds of thousands of cores, so you can parallelize the operation. So these CUDA kernels are basically built for splitting the problem and executing them in a parallel way. So at compile time, you are attaching with each, let's say you have a transformer architecture. So you have lots of operations that we saw, like matrix multiplication, softmax, normalization. So they have written custom code for each type of GPU that they provide. And while compiling a model, you're telling it beforehand that use this function if you're using 8NG GPU or A100 or V100, so tons of GPUs families, tons of GPUs that they have. So at compile time, you're choosing the best function to apply for that particular operation, which is compute heavy. Now, overall, this is the, I will say, the format optimization or compile time operation that you call, and this is from the different kind of operations that NVIDIA TensorRT utility provide. We have a trained neural network. It can be a transformer or a image resonant kind of, or inception, or any kind of architecture. There are lots of custom functions to optimize this, the CUDA kernels. So first you basically do quantization and kernel tuning, and there are lots of other steps which I'm skipping in this talk because we have very limited time. But overall, the idea is you compile it, you have a very optimized inference engine dedicated for a particular hardware, and this file will be the one which will be used for inferencing. Now, the last section of this talk, the state-of-the-art techniques. So in 2023, majority of the research, along with LLM architectures, I won't say much has changed on the architecture side, just like things on the uh, positional embedding side, or normalization techniques, pre-norm instead of layer norm or RMS norm. So minor things have changed, but majority of the effort and research have been focused on how to optimize this inferencing for large deep learning models. And so before we jump into the SOTA techniques, a quick look at the transformer architecture. So this is your encoder decoder architecture with models like BAR T5 EUs, which are sequence to sequence model. But for GPT, Llama, these kind of models, architectures, they're decoder only models. They don't have this encoder stack. You just have your prompt, you enter here, and the one at a time, you will generate a token and you will iterate over it. So let's say I give a prompt like, where is the World conference? So it will generate one token at a time, like say city, then the state name, then the country name, and dates and time and everything. So one token will be generated. It will be again recursively provided to a decoder, and you will recurse over it. And at very high level, all these architectures are made of are attention blocks, which comprise of these. This is your multi-headed attention block where you have the input. Input is transformed into a query matrix, and you have the value and the key matrix, and you take a lot of dot products. You have some feed forward layers, then you have normalization layers, the layer norm ones, and finally you have the softmax layer. So these operations are just repeating in blocks. But the core at the heart of it are this multi-headed attention. So in each layer, you have lots of key value and query matrices. So now question comes, how to optimize this architecture or inferencing this architecture so that you can bring down the latency. So for majority of production settings, whether big companies which like Fang or even lots of social media company or e-commerce companies, the main concern they have is latency. So if you have very large transformer models and you use them, they excel at a lot of tasks. But the issue is if you host them in cloud or like let's say in-premise hosting or whatever you use, the issue is if they're taking seconds to respond, you can't use them in production setting. So the customer experience will be very bad, whether you're using for ranking, search, let's say, or tagging. So there are tons of application, but the core bottleneck is again latency. So that's why this year, a lot of research was focused in deep learning space on optimizing inference. Now, the first technique, I will say, comes back with the model servers. Modern day model servers provide this server-side dynamic batching, and NVIDIA Triton model server I think they were the first one to introduce it. So GPUs are really good at dealing requests in batches. So as I was saying earlier, mentioning that a lot of time when you are training or you are inferencing, if you run a profiler and check your GPU usage, you will be surprised that it's heavily underutilized. And the core reason is it can, as we saw, like 312 teraflops, which is a huge number, the compute capacity. So if you have one request, let's say you have an image or a text statement, and you are using some transformer architecture to basically do some inference. So you'll do the forward pass on your transformer model graph, you'll get the output, but your GPU will be heavily underutilized. So what if you wait for some time? Let's say you have a TTL timer that I will wait for 500 microseconds or 1 milliseconds. And you have the model server queue, which we earlier saw. So requests are coming and we are not even submitting to our model server or to our GPU. We're just waiting. So it's called dynamic batching. On the runtime, we are collecting the requests. And as soon as we hit the timer, or as soon as we hit a max batch size, let's say in this case it was 3, then we'll submit it to the server. The model server will create a batch and then submit to GPU this is where GPUs excel, the throughput, like how many requests you can serve in 1 second. So here in this plot, you will see that normally it's almost same behavior you'll see with different architectures, that with minimal increase in latency from, let's say, 2 milliseconds, 7 milliseconds, the throughput becomes like 24 times. And now you are serving in 1 second. And with, I will say, these days, like majority of the companies, the queries per second, or TPS, transaction per second, they receive. Let's say your e-commerce company or ads company, you have like thousands of requests coming every second. So if you batch them properly, so you want high throughput with a latency benchmark that all requests should return results in, let's say, 7 seconds. And now you are serving 24 requests per second. So throughput is along with latency, is a very big concern for majority of companies. Now, along with dynamic batching, another breakthrough, I will say, which had a very awesome impact on serving latency, model serving latency, was continuous batching. In this technique, what's happening is, let's say when you submit a prompt to ChatGPT or Llama, Bard, or any LLM. So again, as I was saying, that they won't submit your request to the model server instantly. They will generate a batch. So like we just saw in dynamic batching. So now you have, let's say here you have batch of 4, and the yellow coloring is used for prompt tokens. You have four different requests, and each is of different length, because prompts can be of different length. The input to any model can be of different length. Let's say it's a text classification models. So you can have one request with like 3 tokens, or 2 tokens, 3, 4. You can have different length requests. So when your batch is formed, the input batch has different length. Now, when it's your model, your decoder stage, you're generating next token, and the whole batch, the GPU is processing the whole batch right now. So it will generate the blue tokens are generated tokens. Like for this prompt, it generates the next token to predict, which is predicted, and keep on predicting. Then all of a sudden, end of token, the end token was generated for this third request. Then it means we now the transformer won't generate any further output. It has stopped now for this particular request, third request. But second request is we keep on going for that, and then so we are receiving the end token at different time steps. So what it means is, for all these time steps where let's say the third request stopped, then the first request stopped, then the fourth request stopped, GPU was sitting again idle. It's just processing this request now. Now to overcome this, this concept of continuous batching was introduced, that when something, let's say the third request, when the end of token has been detected, a new request will be inserted here. So we will try to basically pack our batch fully to fully utilize the GPU. That the request, the fifth request prompt token will fill this space now. Then this ended the first request, then we have the sixth request from the queue. So you will have some thread, a dispatcher thread will keep on pulling requests from the queue and keep on monitoring the state of your batch, and then handle that. Now, next technique is model compression. So it has been seen over and over that large language models have intrinsic low rank. What we mean by that is they are over parameterized. When we say some LLM is like 13 billion parameters. So, but do we need that many parameters? Maybe it has overfitted on some particular topics because they are learning on large window topics. So whether it's an LLM or even I will say not that huge transformer, let's say it's a BERT itself, which is like around 130 million parameters. So even in those models, if you take a weight matrix at any layer, any attention layer, let's say, or any feed forward layer, and you use singular value decomposition kind of techniques, you take the low rank decomposition, find the k most, I will say, the singular values, the largest singular values, and you basically break this large weight matrix in two smaller ones. Now, when you do a forward pass, you have your input. You don't multiply your input with this weight matrix, but with these two. So net number of computation will be way less than the older flops that were required in the previous settings. So here on the right hand side, here I took the Google Flan T5 base, which is 250 million parameter model, and Flan T5 large, which is 750 million. And what I did was, at different layers in the architecture of the decoder, like sometimes 6th layer, sometimes 12th layer, I took one of the attention heads and took the key or value matrix and performed SVD on that and saw the singular value spectrum. So you'll see that this is for T5 large, has matrix dimension, this M cross N, it's 1024 cross 1024. So you have the singular values. Only the first, I will say, first half dominates. After that, it declines very significantly. Singular values become very, very low. It means you can take K as, let's say, half of this, 1024, and still, when I further checked, the model was, the compressed model was performing almost equivalently as equal as the larger model. Now, another major breakthrough in large language model, as well as any, I will say, can be used for any generative transformer, any language model, is multi-query attention. So earlier we saw the transformer architecture, and at each layer, as I was saying, there's each attention layer has multiple heads. So you have your input. Input is transformed into query matrices, and then you take dot products with key and then further with value matrix after normalizing. So each layer have multiple heads, let's say 8 heads. Then each head will have its own copy of key and value matrices. So this leads to bloated, like your memory needs will be huge for, depending on the transformer architecture. If you have lots of heads, 8 or 16 or 32, if you increase the heads, your performance will increase, but so will the memory requirements. So what they did in multi-query attention is, at any particular layer, they fix the key and the value keys. So if you, in one layer, if you have, let's say here, 8 heads, all the heads will share this key and value matrices. So now your memory requirement has significantly scaled down. So this gives you a very high throughput, and plus the latency impact is way low. Furthermore, again, hammering another technique which was very beneficial for inferencing was a technique called KV caching. So here, as I was saying earlier, discussing the that in each layer we have multiple attention heads, and we have query, key, and value matrices. And in last approach, we saw that we can reuse these key and value. We can share them in a layer across different heads. So with this approach, what they started doing is just caching them. So in a LLM or in a transformer architecture, when it's generating tokens, so in the output stage, it generates one token. Basically, generation is iterative. You will give it a prompt, it will generate the next word. It's just predicting the next word. Then ingest your initial prompt plus the next word it predicted, and again take it as input, and then try to predict the second word. So this will keep on going. So at each iteration, we'll need to reuse these key and value matrices, and their size will change depending on the length of the prediction. So this is just a system-centric technique where you keep on, first you store the pre-computed, for each layer, you have key and value matrices. So when the input sequence comes, you project it on your query. Every head has a different query projection matrix. You get the projection, you look in the cache, get the key and value for your layer, do the dot product and stuff. Do you have a new token? Append that token here. So your cache is regularly updated, and you don't need to recreate these matrices again and again every time you go through the decoder. Now, the last technique that I want to discuss, which I will say was the most impactful, in the language model inferencing, bringing the latency down. Big breakthrough was VLLM. So what VLLM is doing is they identified the performance of LLM serving is bottlenecked by the memory. So the KV cache that we just discussed, they are very, very large sometimes. For Llama 13 billion parameter model, the KV cache itself sometimes constitute 1.7 GB. For a single sequence, when you have a batch of, let's say, 8 requests, then it will be, let's say, around 10 GB, just the memory itself. So during inferencing consumes lots of memory because of these KV, the matrices, the key value matrices that you have to store. Main reason is again that we have to iterate over the decoder stack again and again to generate the next token. So they solve this problem going back to the old-fashioned operating system optimization way. So they introduced a concept called paged attention, which addresses this problem. An attention algorithm inspired by classic idea of virtual memory and paging in operating system. So unlike the traditional attention algorithms, paged attention allows continuous continuous keys and values in non-contiguous memory space. So it's the how the virtual memory OS operates the paging and the virtual memory space. They applied those system-centric algorithms approaches to transformer inferencing. Like when we are caching it, how to offload from GPU cache to the DRAM, then how to again read in the paging kind of scenario. And this basically, if you look here, this is a comparison. And this is, I think, one of the best right now approach for model inferencing, VLLM. The inferencing solution that they provide, if you check their site, is way, way efficient than the biggest name in transformer, the Hugging Face inferencing, the Hugging Face text inferencing, text generation inference. The Hugging Face provide two different inferencing solutions. So they are like 14 to 24x times higher throughput than the Hugging Face one because it's operating system heavy. I will say they borrowed this paging schemes and how virtual memory is handled from operating system domain to the model server domain. So in future, what's in future for inferencing space? So as I was saying, these just off in 2023, what happened? There a lot of work going on a lot of system-centric work, a lot of architecture-centric work, a lot of compiler-specific centric work to tame latency of large language models and large transformers. So what we see in future is one common theme, that shortage of GPUs. Right now, like NVIDIA dominates this vertical, although new players, AMD and Intel, are coming into the market, but big companies, cloud companies, they hog a lot of GPUs. So there's a consistent, you will see shortage of A100, H100 GPUs, which are the latest state-of-the-art GPUs from NVIDIA. So this we foresee. Second thing is the intense energy usage and the carbon footprint. So you will all these extremely powerful GPUs, and when you have racks of them and you're running these powerful models, so they consume lots of energy. The same thing was seen like during Bitcoin mining days, that when people were doing Bitcoin mining at scale using GPUs, so energy consumption went super high. And the third thing which we can foresee is that because of privacy concerns, like Apple has released a lot of privacy laws that they won't share customer data. So running models on cloud or on external servers, machine learning models, they will require a lot of features. So in runtime, you can't get those features because of privacy concerns from user end. So running models on edge devices will be the next frontier. Actually, a lot of federated learning is another area where a lot of research has been going on. That how can you run models, powerful models, on your Apple phone or let's say Android phones, and utilize the phone processor to perform inferencing. Yeah, overall, I think we're at the end of it. Any questions?
So thank you, Siddharth, for your wonderful session. So audience, if you have any questions, so feel free to ask. Madam, sir, I think it is in chat box. Some they have written. Siddharth, they have written on chat box. Check.
So there's a new neuron. Yeah, so Amazon is also investing heavily for basically making custom chips for model inferencing. So the whole problem, like Google has invested a lot on TPUs too. Now Facebook is also investing, big companies. As I said, one common area everybody is seeing and anticipating in future, the one common issue is shortage of GPUs and the monopoly over GPUs by mostly NVIDIA. So that's why a lot of cloud-based companies which provide cloud solutions like AWS, Google, they're investing heavily in this space. So all these architecture are right now, of course, they can't compete with A100, H100, the state of the art, but they provide a sweet spot in a lot of areas. They are very cost effective, first of all, these solutions. Let's say you, mostly for industry applications, let's say you have some query classifier for e-commerce or a ranking model, recommendation model. So those models, I would say 90%, no more than 90% of model used across in the industry. Sentiment classifier, text classifier, summarization models, they are not that huge. Like they are not 7 billion, 13 billion, or like 70 billion parameter models. So it's overkill to use, let's say, 800 GPU for that. So these kind of architectures are the best bet, like the, I will say, best bang of the buck kind of scenario.
Should come there.
Yes, you come here.
Echo is coming. Thank you, Siddharth Sharma. That was an enlightening talk for all of us. I wish to know, if we build a model, let's either in TensorFlow or PyTorch, as an end user, we developed a model, and suppose we wish to do some optimization at our end. What are the choices that are left for us? Because we are not working at the level that you have presented, like that. Those are for industries, the production level things, right? Let's say for academia and students projects, what kind of optimizations do you suggest out of these?
So the first thing I will say is, let's say you have trained a model, you have your own custom architecture. So let's say for the sake of it, you are building a, let's say, ranking model, or you're trying to explore new architectures from you took BERT model and you are trying to add some skip connections, or you have some new module or computation layer that you're adding. So when you have your own custom architecture, the first thing is go heavy on profiling, use PyTorch profiler. And what that will do is, and there are a lot of awesome visualization schemes, the heat maps and stuff. They will tell you where are the bottlenecks. So you will literally see that the peak memory load, or where your model, your CPU or GPU is sitting idle, what's happening. It will see that it's doing a lot of tensor transformations. It's just reading a lot of data from disk to memory, or you have some two very heavy matrix multiplication is going on. So it will literally show you the Matmule operation that's literally hogging all your computation power. So then here you will have to hit, let's say you have a feed forward layer and you have extremely large output size, like the 1024. So then you can basically try to play around, let's say I load down the size of 512. What will happen? Then you again run the PyTorch compiler. But lots of, like, this will be open, I will say, playground that run the profiler again and again, and likely and similarly NVIDIA has Semi and other profilers that when you run your model on GPU, they will tell you layer by layer. You can see dig in depth, like layer by layer, what's happening, which operation is taking most of the compute time, which operation is hogging on the memory, or which operation where sometimes you will say it's not your model architecture, it's just limited GPU RAM, let's say. So a lot of GPU is offloading lots of model weights to, or a lot of data to CPU RAM, then reading it again. So maybe better CUDA kernel is your solution. So you can write your own CUDA kernel for that. But apart from these, I will say do heavy benchmarking. Use some of like Onyx or TensorRT kind of formats. They have tons of custom optimizations. So they will read your model architecture. They will saw that, let's say in PyTorch, you have two matrix, A and B. You are summing them and you're multiplying by, let's say, third matrix. So what these advanced tools, TensorRT or Onyx, these model formats will do is they will take your PyTorch graph and literally they will change the model graph. They will merge multiple operation into one single operation. And then if you are running on GPU, yep. So there are off the shelf lots of solutions which will save you lots of time and I will say energy. But as a learning experience, it will be really good if you go step by step and then use these custom tools and see what changes they have done. So if you run, let's say, format conversion, the compile time optimization that I was saying, to your model to Onyx, so Onyx will literally print on the console what it's doing. And it is wonderful to see that hundreds of changes on even very simple, I would say, off-the-shelf architecture like BERT. So let's say for a Hugging Face, you imported BERT model and you convert it to Onyx, you will see tons of optimization it's doing. And then if you use TensorRT, is furthermore heavy on the GPU side. So that will be a good starting step, like to see what are these off-the-shelf utility tools are doing to your model graph. So then you can go back and next time, like, don't make these kind of mistakes.
Thank you. Another quick question is, as you were pointing out the carbon footprint due to usage of these GPUs, what are your opinions on using some quantum computing techniques for these kind of computational intensive tasks? Do you see any advancements happening there, and what is the kind of carbon footprint compared to the conventional GPU or TPU kind of?
I'm sorry, I'm not well acquainted with that area.
Okay, thank you. Thank you very much.
No, thank you. Thanks a lot for your question.
Hello, Siddharth. So we have some more questions on chat box. So what do you see?
Oh, yeah. Yeah, actually, these for CNNs, there already been a lot of work, and I think you'll find a lot of tooling also for this thing to find for custom architectures, like standard architecture like Inception, ResNet, or VGG. Or there's a pretty standard, like once you have the architecture, there you have the kernel filters, then you have the nonlinearity applied, then you have the pooling done. So each step, I mean, you don't need to do by hand. I can't remember right now, but there is a lot of tooling available which can tell you in one forward pass what each layer, what operation, how many flops it's consuming, because you have fixed input size for the image tensor, and you have those the convolution kernels, and what I'm trying to say is there's nothing dynamic. Everything is fixed in these architectures, so it's very easy to compute.
Good morning, sir. I have a question about the architectural changes. Like taking the pre-trained model, are there any techniques which can be employed so that the architecture of these models can be tweaked a little bit and then used for fine-tuning purpose?
So for fine-tuning, I will say the go-to strategy, mostly the most popular one, is adapter-based fine-tuning. So like started with LoRa, now like a lot of variants are available, even dynamic adapters are available. So what you do is, let's say you have one base model, let's say you use Llama, and it's like 8-bit quantized. So you can basically fit in your default GPU RAM, or even I think CPU RAM, it will fit the 8-bit quantized 7-bit checkpoint, 7-bit parameter checkpoint. So now this is a quantized version in low bits. So when you want to fine tune it, you basically add additional feed forward layers, not in between, but parallel to the architecture. So when you provide an input, you freeze your original transformer. You won't update its model. You can't, it's too big to train on more of like GPUs available to normal consumers and users, or the computational resources that you must be having. So it will take you months to fine tune it if you have sufficient data. So you take basically heavily quantized, like 8-bit quantization llama checkpoint from, let's say, Hugging Face. You freeze it, you're not updating it, and you are adding additional adapters. Adapters are just some feed forward layers that you are adding to it, not in between the layers, but on the sides. So when you provide an input, you will get the output of your llama models, let's say one layer, and you have an adapter attached to that layer. So you'll provide the same input to the adapter too, then you merge them. And these adapters are, I will say, their number of parameters. That's why they became popular, this technique, adapter-based learning. So they call it low rank adapters because, as I was saying in model compression, that you don't need large weight matrices. They use very small matrices. Like original llama, let's say it has 1024 cross 1024 weight matrix at a particular layer. So here what you do is 1024 cross 10, and you have 10 cross 1024, two weight matrices, low rank. So you forward your input through these layers too, and then you add it to the output of the llama's layer. So in a way, you are learning these very low rank, less parameter adapter weight matrices and keeping the original model intact. So that's like LoRa based, adapter based learning is the de facto standard right now for fine tuning these models. You can basically take a Google Colab, take a free TPU there, and this 7 billion parameter 8-bit checkpoint of llama, you can easily fine tune it for your use case.
Thank you, sir. Can we safely say that there is no scope or a very little scope to change the architecture in between layers for these models?
You can try, but again the issue will be to fine tune it. Let's say you change the architecture, you added new layers on some new type of computation. To fine tune these models, then you need distributed training setup. So then you'll have to visit the like AWS or GPU, some cloud where they have infrastructure for distributed training. So it will be either you have like extremely powerful GPUs in-house, or you are utilizing. That's why all these LLM space is more monopolized by big companies. It's very hard for let's say universities or individuals to experiment with these. More because of the computational part.
Thank you, sir. Thank you for your answer.
So one more key question in the chat box, sir.
It's good choice to follow PyTorch framework for. Yep, actually, when I was working at Meta, so Torch Vision, the PyTorch is a library for handling um, uh, vision-based model. It's heavily used there for applied applications. Torch Vision is I think I used it long back for some minor fine-tuning tasks on ResNet, but it was very easy to use, like modern Hugging Face transformer libraries for text. Torch Vision has most of the, like in the model hub, you have all the, I think, majority of the architectures there. So it's very easy to fine tune. How can models not explicitly mentioned in the documentation? I haven't personally used Neuron. I still have to, like, this is one thing on my agenda. Even I have to try it. They have their own, yes, I know they have their own format, like the format optimization I was discussing earlier. Sorry, I haven't tried explicitly the neuron-based inferencing. Yeah, so again, this model conversion from, let's say, PyTorch or TensorFlow to a particular format. As far as I know, not all the models are supported by most of the tools like Onyx or TensorRT. They also have their teams. Why they are not supported? Because when you are converting, like, let's say model architecture is there, like ResNet versus, let's say, a BERT architecture. So when you are using these tools, Onyx or TensorRT, or let's say the Neuron one also, and converting the format, there are lots of operations for which maybe the CUDA kernel is not available. So first, NVIDIA will have to invest in developing that particular CUDA kernel that can perform that type of computation. Then these formats will optimize over that and basically the model graph, let's say, as I was saying, like there is operation where you are adding two matrices and multiplying with a third. So they will fuse these operations and let them go in one go. So when you have a new architecture, unless until downstream these companies are providing support, let's say NVIDIA will first write CUDA kernel, then somebody will change in open source community the Onyx support for that model. Then finally you will be able to use it. So it's not like all any type of model you can basically optimize this format using the Onyx or TensorRT or these kind of utilities. But still, I think Onyx is the open source model format. It still does lots of I will say majority of the optimizations, not extremely high level granular optimization, but I will say the commonplace things it will take care of that. So maybe you can try Onyx first and on this model and then see how it is doing. It will provide a really good benchmark for you on the inferencing side. I think so, but I will have to check the Inferentia. I haven't tried it personally. That's what I was saying, but I can check.
Okay, so once again, thank you very much, Siddharth, for agreeing
Most welcome.
to become the eminent speaker for our Wadla 3.0. So hope in future also we would continue to call you. Okay, so the
Sure.
talk which was really amazing. A lot of like insights you have highlighted in LL, the recent advanced topics. So once again, thank you very much, Siddharth.
Thank you. Thanks a lot for the invite.
I think we can close this session now.